Bismillahirrahmanirrahim. In our last classes, we discussed about the vector analysis. In today's class, we will talk about the Coulomb's law and electric field intensity. This is our chapter number 2 from the book Engineering Electromagnetics by William H. Hart. So in this chapter, we will restrict our attention to static electric fields in vacuum or free space. So we will begin this chapter by describing a quantitative experiment performed in the 17th century, and that is the experimental law of Coulomb. So Coulomb's law states that the force between two very small objects separated in vacuum or free space by a distance which is large compared to their size is proportional to the charge on each and inversely proportional to the square of the distance between them. So if we have two very small objects separated in a vacuum by a distance which is large compared to their size, so there will be a force of attraction or a force of repulsion, and that force will be equal to the product of their charges and inversely proportional to the square of the distance between them. So the force will be directly proportional to the product of their charges, and that force will be inversely proportional to the square of the distance between them. So if we change the proportionality into equality, so F will be equal to K Q1 Q2 divided by R square, where Q1 and Q2 are the positive or negative quantities of charge. R is the separation and K is a proportionality constant. If the international system of units is used, so we know that the charge is measured in coulombs, the distance will be measured in meters, and the force should be in newtons. So this will be achieved if the constant of proportionality K is written as K is equal to 1 divided by 4 pi epsilon naught. The factor 4 pi will not appear in the denominator of Coulomb's law, but will not appear in more useful equations, that is including Maxwell's equation, which we will obtain with the help of Coulomb's law. So this term 4 pi will only appear in the denominator of Coulomb's law, but when we will extract Maxwell's equation by the help of Coulomb's law, this factor will not be appear there. So the new constant epsilon naught is called the permittivity of free space and has the magnitude 8.85 into 10 raised to power minus 12 farad per meter. We have already discussed about the permittivity of free space. It is the property of a material medium to restrict or to oppose the electric lines of force to pass through it. So it is the opposition offered by a material medium to restrict or to oppose the electric lines of force to pass through them. So this is called the permittivity of free space, and it is related to the electric fields, and its value is 8.854 in 10 raised to power minus 12 farad per meter. The quantity epsilon naught is not dimensionless because Coulomb's law shows that it has the label Coulomb square per Newton into meter square. It means that अगर ये वैल्यू हम इसी इक्वेशन में पुट कर ले और उससे एप्सिलॉन नॉट की वैल्यू निकाले, so that will be measured in Coulomb square per Newton into meter square. So we will measure the permittivity in farad per meter. So Coulomb's law is now F is equal to Q1 Q2 divided by 4 pi epsilon naught R square. Now if we look at this equation, the force is measured in coulombs. The force is measured in newtons. The unit of charge is coulomb, and the distance is measured in meters. Now, how can we define a force of 1 Newton? So, let's suppose if we have a mass of 1 kilogram and if an acceleration of 1 meter per second square is produced in this mass. So, the force required to produce this acceleration in a mass of 1 kilogram will be 1 Newton. So, it is the force required to give a 1 kilogram mass an acceleration of 1 meter per second square. And if we represent this 1 Newton force in pounds, so 1 Newton is equal to 0.2248 pound. We have already discussed that the unit of charge is coulomb, and coulomb is really a big amount of charge. It means that if we have charge objects, each having a charge of 1 coulomb, and if there is a separation of 1 meter between them, so the force between these two charges will be 9 into 10 raised power 9 Newton. That means that if we have two charges of 1 coulomb each, and if the separation between them is 1 meter, so the force between these two charges will be equal to 9 into 10 raised power 9 Newton. So coulomb is really a big amount of charge. As we take the smallest amount of charge, that the charge of electron. मतलब इलेक्ट्रॉन पे जो चार्ज होता है, so we take that charge as the smallest charge. We have already discussed about these things in our previous classes. Now, in order to write this equation in vector form, so how can we write this equation in vector form? So in order to write the vector form of this equation, we need the additional fact that the force acts along the line joining the two charges and is repulsive if the charges are alike in sign and attractive if they are of opposite sign. So if we look at this figure, let's suppose the charge Q1 is located at this point having a position vector of R1. The position vector of the charge Q2 is R2. So the line joining these two charges will be R12. So if we represent these distances in vector form, so the position vector of Q1 will be R1, the position vector of R2 will be, the position vector of Q2 will be R2, and the distance between the two charges will be R12. So in vector form, R12 will be equal to R2 minus R1, because this vector plus this vector will be equal to this vector. So R12 will be equal to R2 minus R1. So if we write that equation in vector form, so the force will be acting along the line joining the two charges. मतलब इन दो चार्जेस के बीच जो लाइन है जो इन दो चार्जेस को ज्वाइन कर रहा है, तो फोर्स भी उसी लाइन पे एक्ट करेगा, because this is F2. This force is being experienced by the charge Q2 due to Q1. F2 is the force that is being experienced by the charge Q2 due to Q1. So F2 is acting along the line joining the two charges. So let the vector r1 locate q1 where r2 locates q2. Then the vector r12 will be equal to r2 minus r1, and that represents the line, the directed line segment from q1 to q2 as shown in figure 2.1. This is actually figure 2.1. The vector F2 is the force on Q2 and is shown for the case where Q1 and Q2 have the same sign. So the vector form of Coulomb's law is F2 is equal to Q1 Q2 divided by 4 pi epsilon naught R12 square into A12, whereas A12 is a unit vector in the direction of R12, and we know that the unit vector is equal to the vector divided by its magnitude, and this vector r12 is r2 minus r1, whereas r2 is the position vector of the charge q2 and r1 is the position vector of the charge q1. So the unit vector a12 will be equal to the vector divided by its magnitude. So this was all about the Coulomb's law, that if we have two charges that are separated by a distance r, so the force of attraction or repulsion between these two charges will be directly proportional to the product of their charges, and this force will be inversely proportional to the square of the distance between them. So this force F will be equal to Q1 Q2 divided by 4 pi epsilon naught r. So this was all about the Coulomb's law. Now we will discuss about the electric field intensity. So as we already discussed that, let's suppose we have two charges Q1 and Q2. Now अगर इसी एक चार्ज Q1 को हम फिक्स कर ले और Q2 को हम मूव कर ले in any direction, so this Q2 charge will experience a force. This Q2 charge will experience a force. A force will be exerted on this Q2 charge at different points. So this Q2 charge is actually displaying the existence of a force field. Now call this second charge as a test charge. और test charge का क्या मतलब है? It means that the magnitude of this charge will be very small as compared to the source charge. अगर Q2 को हम टेस्ट चार्ज बनाते हैं तो Q1 हमारे पास सोर्स चार्ज होगा और Q2 चार्ज का मैग्नीट्यूड इतना होना चाहिए जिसका फील्ड इसी Q1 चार्ज को इफेक्ट ना करे. So if we now consider one charge fixed in position, say Q1, and move a second charge slowly around, we note that there exists everywhere a force on this second charge. In other words, this second charge is displaying the existence of a force field. Call this second charge a test charge Q3. So the force on it is given by Coulomb's law. Ft, the force on the test charge will be equal to Q1 Qt divided by 4 pi epsilon naught R1t whole square into A1t. Like in our previous case, we had taken two charges Q1 Q2. So मैंने आपको बताया था कि जो force है that is F12 and this force is experienced by Q2 due to Q1. अब अगर हम इसी Q2 चार्ज को टेस्ट चार्ज बनाएं, इसको हम Qt कर ले, so this force will be F1t and it is the force experienced by the test charge due to this charge Q1. So Ft will be equal to Q1 Qt divided by 4 pi epsilon naught R1t whole square. Now writing this equation as the force, now writing this force as a force per unit charge. So Ft divided by Qt will be equal to Q1 divided by 4 pi epsilon naught r1t square into a1t. If we take this equation as the force per unit charge, the force per unit test charge, so it will be equal to q1 divided by 4 pi epsilon naught r1t square into a1t, whereas a1t is the unit vector along this line r1t. So the quantity on the right hand side is a function only of q1 and the directed line segment from q1 to the position of the test charge. It means that this is r1t. So it is a directed line segment from q1 to the position of the test charge. This describes a vector field and is called the electric field intensity. This describes a vector field and is called the electric field intensity. So if we look at this equation, अगर इस equation को हम देख लें तो जो left hand side है Ft divided by Qt, the force per unit positive test charge, this is actually the definition of electric field intensity. Whereas the right hand side represents the expression of the electric field intensity due to a source charge Q1. If we have a source charge Q1, so its expression will be given by this equation, Q1 divided by 4 pi epsilon naught R1 whole square into A1t. I am repeating it again, that the left hand side actually represents the definition of the electric field intensity, and that is the vector force on a unit positive test charge, whereas the right hand side represents the expression of the electric field intensity due to a source charge Q1. So if we have a source charge Q1 that is placed at some point, so due to this source charge Q1, we can find the electric field intensity at this point, we can find the electric field intensity at this point, we can find the electric field intensity at this point. So let's suppose if we have a source charge Q1 and this distance is R1. So at this point, the electric field intensity will be equal to Q1 divided by 4 pi epsilon naught R1 square, whereas A1 will be the position vector of this line. So A1 will represent the direction of the electric field intensity, because electric field intensity is a vector quantity. So the quantity on the right hand side is a function only of Q1 and the directed line segment from Q1 to the position of the test charge. This describes a vector field and is called the electric field intensity. We define the electric field intensity as the vector force on a unit positive test charge. We would not measure it experimentally by finding the force on a 1 coulomb test charge. However, because this would probably cause such a force on Q1 as to change the position of that charge. जिस तरह पहले भी मैंने आपको बताया कि अगर एक पॉइंट पे हम इलेक्ट्रिक फील्ड इंटेंसिटी फाइंड आउट करना चाहते हैं ड्यू टू सोर्स चार्ज, तो अगर उसी पॉइंट पे हम एक 1 कूलम टेस्ट चार्ज प्लेस कर लें, सो 1 कूलम टेस्ट चार्ज इज एक्चुअली अ बिग अमाउंट ऑफ चार्ज, सो इसको हम उसी पॉइंट पे हम एक्सपेरिमेंटली इलेक्ट्रिक फील्ड इंटेंसिटी फाइंड आउट नहीं कर सकते, बिकॉज it would exert a force on the source charge, and due to which the position of the source charge will change. So test charge normally हम एक small amount of charge लेते हैं जिसका जो फील्ड होता है वो सोर्स चार्ज के फील्ड को इंटरप्ट ना करें, डिस्टर्ब ना करें. So electric field intensity is the force on a unit positive test charge. This is the definition of the electric field intensity, and the expression of the electric field intensity is given by this equation. So equation number 7 is the defining expression for the electric field intensity, and 8 is the expression for the electric field intensity due to a single point charge Q1 in a vacuum. In the succeeding sections, we shall obtain and interpret expressions for the electric field intensity due to more complicated arrangements of charge. It means that if we have a number of charges, or if we have a continuous amount of charges, like if we have a line charge density, surface charge density, volume charge density, how can we represent the electric field intensity due to this contribution of charge? So let us first dispense with most of the subscripts and add, reserving the right to use them again anytime there is a possibility of misunderstanding. मतलब अगर हम इस इक्वेशन को देख लें, सो यहाँ पे बहुत सारे सब्सक्रिप्ट्स लिखे हुए हैं, Q1, R1T, A1T, तो इन सब्सक्रिप्ट्स को फिलहाल हम रिमूव कर लेते हैं. सो द इलेक्ट्रिक फील्ड इंटेंसिटी विल बी इक्वल टू Q डिवाइड बाय 4 pi epsilon naught R square into AR. We should remember that R is the magnitude of the vector R, the directed line segment from the point at which the point charge Q is located to the point at which the electric field intensity is desired, and AR is a unit vector in the R direction. It means that if we have a source charge of Q that is located at this point, and at this point P, the electric field intensity is desired. So at this point P, the electric field intensity EP will be equal to Q divided by 4 pi epsilon naught R square into AR. If R is the distance of the point from the source charge. So this is the point at which the electric field intensity is desired, and this is the position of the source charge. तो सोर्स चार्ज origin पे भी प्लेस हो सकता है, origin के अलावा किसी और पॉइंट पे भी प्लेस हो सकता है. So we have to look at the position of the source charge, and we have to look at the position of the point at which the electric field intensity is desired. Now let's suppose, let's arbitrarily locate Q1 at the center of a spherical coordinate system. So let's suppose if we have a spherical coordinate system, and at the center of this spherical coordinate system the charge Q is located. So now this, and if you want to find the electric field intensity at the surface of this sphere, so now this R will represent the radius of the sphere, and the electric field intensity at this point P, R at the surface of the sphere, will be equal to Q1 divided by 4 pi epsilon naught R square. Now this R actually represents the radius of the sphere, and the electric field intensity at the surface of the sphere will be equal to Q1 divided by 4 pi epsilon naught R square into AR. So remember that this electric field intensity is actually the radial electric field intensity, because if we select the spherical coordinate system, so this electric field intensity will be the radial electric field intensity, or it may be along the theta direction, or it may be along the phi direction. But from this equation we know that this electric field intensity has the radial component only. This electric field intensity doesn't have E phi, doesn't have E theta. So we have the radial component only. So ER will be equal to Q1 divided by 4 pi epsilon naught R1 R square. So this is the magnitude of the radial component of the electric field intensity. Now, if we have to write this expression in a Cartesian coordinate system. So this expression will become complex because अगर इसी equation को हम देख लें, so this equation has a radial symmetry. और जो हमारा problem है that has a radial symmetry or spherical symmetry. तो अगर एक problem की symmetry spherical हो और उसी problem को हम किसी और coordinate system में solve कर लें, so that problem will become a little bit complex. You will see now. Like writing these expressions in Cartesian coordinates for a charge q at the origin. It means that if we have a charge q that is placed, if we have a charge q that is placed at the origin, and if we want to find the electric field intensity at this point P, the vector is r. Now I am saying that this charge q is placed at the origin. So this r will be equal to xax plus y ay plus z az. Now this is a vector r. This is a vector r. What will be ar? Vector divided by its magnitude. So ar will be equal to vector divided by its magnitude. So the electric field intensity q, we know that the electric field intensity is equal to q divided by 4 pi epsilon naught r square into ar. तो इसको हम किस तरह लिख सकते हैं? r square will be equal to, मतलब अगर हम r square लें तो इसका हम, this is actually the vector, its magnitude is, अगर इसका हम पहले magnitude find out कर लें, so the magnitude will be equal to x square plus y square plus z square under the root. तो अगर इसका हम square लें, so we will take this square, so it will be equal to x square plus y square plus z square. Now अगर हम unit vector को देख लें, so we have xax plus yay plus zaz divided by this term. So this unit vector can be written as x divided by this term into ax plus y divided by this term into ay plus z divided by this term into az. So now if we look at this equation, so the electric field intensity is equal to q divided by 4 pi epsilon naught r square into its unit vector. तो unit vector को हमने अलग अलग लिखा हुआ है, x divided by this term into ax plus y divided by this term into ay plus z divided by this term into az. तो इसी इक्वेशन से हम ex भी फाइंड आउट कर सकते हैं, ey भी फाइंड आउट कर सकते हैं और ez भी फाइंड आउट कर सकते हैं. लाइक ex will be equal to q divided by 4 pi epsilon naught, q divided by 4 pi epsilon naught x square plus y square plus z square into this term. Ey will be equal to q divided by 4 pi x epsilon naught x square plus y square plus z square into this term. Or Ez will be equal to q divided by 4 pi epsilon naught x square plus y square plus z square into this term. So this will be ex, ey and ez components. Now if we look at this equation is a little bit complex. Why this equation is complex? Because एक प्रॉब्लम है जिसकी सिमेट्री स्फेरिकल है और उसी प्रॉब्लम को हम कार्टेशियन कोऑर्डिनेट सिस्टम में सॉल्व करने की कोशिश कर रहे हैं. तो अगर एक प्रॉब्लम की सिमेट्री स्फेरिकल है और उसी प्रॉब्लम को हम कार्टेशियन कोऑर्डिनेट सिस्टम में या सिलेंड्रिकल कोऑर्डिनेट सिस्टम में सॉल्व कर लें, सो दैट प्रॉब्लम विल बिकम अ लिटिल बिट कॉम्प्लेक्स. नाउ अगर सोर्स चार्ज ऑरिजिन पे प्लेस नहीं है, मतलब इफ द सोर्स चार्ज इज नॉट एट द ऑरिजिन, तो फिर जो हमारा प्रॉब्लम है उसकी फिर स्फेरिकल सिमेट्री नहीं रहती. तो अगर एक सोर्स चार्ज है और उसका जो पोजीशन वेक्टर है that is not at the origin, that is somewhere else, so how can we find the electric field intensity if the electric field intensity at a point if the source charge is not located at the origin? ये जो इक्वेशन हमने निकाल लिया, this equation is for the electric field intensity due to a source charge which is placed at the origin. Now if the source charge is not placed at the origin, what will we do? If we consider a charge which is not at the origin of our coordinate system, the field no longer possesses spherical symmetry nor cylindrical symmetry unless the charge lies on the axis. We might as well use Cartesian coordinates. For a charge q located at the source point r dash, we find the electric field at we find the field at a general field point r by expressing r is equal to r minus r dash. It means that, let's suppose we have the source charge that is placed that is not placed at the origin. So the position vector of the source charge is r dash, and the position vector of the point at which the electric field intensity is desired is r. So now the position vector of the charge q is r dash, और जिस point पे हम electric field intensity find out करना चाह रहे हैं, तो इनके बीच जो distance है that is r. And if we represent this distance in the form of a vector, so r will be equal to r minus r dash. Like जिस तरह ये distance मैंने r2 लिया हुआ था, ये distance मैंने r1 लिया हुआ था, so r was equal to r2 minus r1. So now r is equal to r minus r dash. Now इसी वेक्टर r dash को हम किस तरह रिप्रेजेंट करते हैं? x dash ax plus y dash ay plus z dash az, और r को हम किस तरह रिप्रेजेंट करते हैं? x ax plus y ay plus z az. X dash, y dash, and z dash are the magnitudes along the z axis, x axis, y axis, and z axis. And similar is the case with the vector r. So the vector r will be equal to r minus a dash. So r minus r dash. So it will be equal to x minus x dash into ax plus y minus y dash into ay plus z minus z dash into az. So now for a charge q located at the source point r dash, we have the source point and we have the field point. So r dash is equal to this equation and r is equal to this equation. So r will be equal to r minus r dash. So the electric field intensity at point P will be equal to q divided by 4 pi epsilon naught r minus r dash whole square into its unit vector, and the unit vector is the vector divided by its magnitude, because r is equal to r minus r dash. So we know that it is equal to q divided by 4 pi epsilon naught r square, and we know that r is equal to r minus r dash square into its unit vector, and the unit vector is vector divided by its magnitude. So it will be equal to q into vector divided by 4 pi epsilon naught r minus r dash whole cube square into magnitude. So it will become q. So it will be equal to q divided by vector is x minus x dash into x plus y minus y dash ay plus z minus z dash into az divided by magnitude का cube. So magnitude का cube, because this is under root, so it will be equal to square into 3 divided by 2. Like अगर r minus r dash का हम magnitude find out कर लें, so that will be equal to x minus x dash whole square plus y minus y dash whole square plus z minus z dash whole square under the root. तो अगर इसका आप इसी मैग्नीट्यूड का क्यूब ले, so it will be equal to this term into 3 divided by 2, because 1 by 2 is coming from this term. So we will get x minus x dash square plus y minus y dash square plus z minus z dash square whole 3 by 2. So this is the electric field intensity due to a charge q which is not placed at the origin. Now we know that the Coulomb forces are linear. So if we have a number of charges, so the electric field intensity due to 2-point charges q1 and q2 is the sum of the forces on qt, the test charge, caused by q1 and q2 acting alone. So ER will be equal to q1 divided by 4 pi epsilon naught r minus r1 square a1 plus q2 divided by 4 pi epsilon naught r minus r2 square a2. इसी तरह if we have n number of charges. So ER will be equal to, if we look at this equation, if we look at this figure, so at point P, the electric field intensity is desired, and we have many charges. We have Q2, we have Q1, Q2. We can take Q3, Q4, Q5. So many electric field intensities if we have a number of charges. So the position vector of Q1 is R1, and the position vector of Q2 is R2. So, and at point P, the electric field intensity is desired. So we have to look at this distance, the distance between the source charge and the point at which the electric field intensity is desired. I am repeating it again. हमें कौन सा distance चाहिए होता है जो source charge और उसी point के बीच को, मतलब this distance is required and this distance is required. Now, if the position vector of point P is R and if the position vector of Q1 is R1, so this distance will be R minus R1. Now, the position vector of Q2 is R2, so this distance will be R minus R2. Similarly, अगर यहाँ पे कोई और charge place हो Q3, so its position vector will be R3, so this distance will be R minus R3. So इसी point पे जो electric field intensity होगी, that will be the sum of the electric field intensities due to Q1 plus Q2 plus Q3. So ER will be equal to Q1 divided by 4 pi epsilon naught R minus R1 whole square into its unit vector. The unit vector is A1. Similarly, the unit vector is A2. So the net electric field intensity will be equal to ER, and that will be equal to E1 plus E2. So this is the electric field intensity at a point when we have two source charges. इसी तरह, if we have n number of source charges, so the Coulomb forces are linear and the electric field intensity will be the addition of the electric field intensities due to those number of charges. So ER will be equal to this equation. So अगर इसके लिए हम summation sign use कर लें, so the electric field intensity will be equal to the summation of Qm divided by 4 pi epsilon naught R minus Rm whole square into Am, whereas M ranges from 1 to n. मतलब if M is 1, so this will be equal to Q1 divided by 4 pi epsilon naught R minus R1 whole square into A1. इसी तरह Q2 divided by 4 pi epsilon naught R minus R2 whole square into A2, and so on. So this was the electric field intensity at a point due to a number of charges. If you have any question, you can ask. Thank you.